Not at all.
That's right. We're live, folks.
Are we?
Okay. Okay, so linear momentum. This is a natural place to pick up from when we were talking about Newton's laws, acceleration, net force, friction, things like that. Well, once an object is moving and has that acceleration, there's a momentum. And when you have a change in momentum exerted by a force or force over time, you have words like impulse and collision and so on. So this is kind of an extension of where we left off first semester. So just want you to kind of pay attention in here. And also these notes will also be posted. Mr. Joe will post the notes at the end of today's class. So the video and
Video, like I've been doing. I've been posting the videos and I've been posting the PowerPoints that he's been using. So both will be posted.
PowerPoint and video. All right, and I realize some of this is review. So this is to reinforce what you've already learned, or if you didn't really learn it the first time and it's new, great, now you know it. So it's a win-win. So momentum. To find momentum, you can do mass times velocity. Do you remember why are these variables bolded? Why is there a little arrow over top of it? What does it mean? They're vectors. Vectors have magnitude and direction. A momentum, like a velocity, can be in the positive or negative direction. Mass is just a scalar because you can't have a negative mass. It doesn't make sense to have negative 2 kilograms. All right? So just writing some equations over here. We've got momentum is mass times velocity, so a change momentum is mass times change velocity. Also here, the sum of all forces can be found by looking at the change of momentum over the change of time. You might also recall that we just had an equation that used the sum of all forces, which equals mass times acceleration. Well, if the net force can equal a change of momentum over time, and it can equal mass times acceleration, you can set these equal. And it turns out when you have a mass times acceleration, which is a meters per second squared, or whether you have a change of momentum, which is a kilogram meter per second divided by time, it's really the same thing. So units for momentum are often represented as kilogram meter per second, which can also be written as a Newton times second because it's also a force times time. So there's different ways of writing the same thing. All right, that was from Newton's second law. When objects have momentum and they collide, during the collision, the momentum doesn't change. If you have the same momentum before and after a collision, you have what is known as conservation of momentum. So for conservation of momentum, momentum before equals that momentum after. And how many times you write mass, velocity, and how you write it depends on the situation. Not every situation is the same. So for instance, in this case, we have, that's the mass A times velocity of A collides with mass B moving at a velocity of B. That happens before the collision, but after the collision, you have mass A moving with a different velocity and mass B moving with a different velocity. And again, this is one way to write it for when the two objects do not stay together. But let's say they collide and the objects do stay together. Well, this would be an example of, for instance, an elastic collision. An example of an inelastic collision. You might write this as MAVA plus MBVB equals MA plus MB B prime. Looks like a whole bunch of letters. It looks more complex than it is. We're going to do some examples using that, and it'll make a lot more sense if any of this confuses you right now. This is just saying the mass times velocity of each object before equals the total momentum after. You're just doing mass times velocity for each object. For example, howdy. Conservation of momentum when we have these two look like little train cars or box cars here. Train car A is rolling, train car B is stopped. When A collides with B and they stick together, they're both going to roll off with some momentum. The momentum that the two have as they roll off together will be the same momentum that A had to begin with. What do you think about the velocity? A is rolling at 24 meters per second. What do you think the velocity will be with A and B? Will it be more or less than 24 meters per second? Should be less. Conservation momentum means momentum before equals momentum after. So if the mass increases, the velocity decreases in order for the momentum to stay the same. Let's suppose that we knew mass of car A and mass of car B were the same. Well, if mass A is rolling at 24 meters per second, collides with B at rest, how fast will they both be rolling to have conservation momentum? If the mass doubles, then the velocity will be half, is what we're looking for there. But even if you didn't know, we're going to do examples and everything's going to be crystal clear. It's going to work out. Conservation of momentum. So when the momentum before equals momentum after, and actually the total momentum stays the same the whole time, also explains how something like rockets work. You can't take, for instance, an airplane to the moon, because what are you going to run out of? You're going to run out of lots of things, actually. But the way an airplane works is you need air, right? There has to be wind, there has to be a fluid to fly through. Well, as you get higher up in the atmosphere, there's less air, there's nothing to push off of. Same thing with a helicopter. You can fly a helicopter because it's like a giant fan, it's pushing the wind down, and you've got a force down, pushing the helicopter up. Well, eventually, if you go up in space, a helicopter's not going to work. You can't fly a plane on the moon, but a rocket works. Why does a rocket work? Well, it's conservation of momentum. Here's a rocket just sitting here, but when that rocket ejects, through combustion, it has fuel, you have these explosions expelling this gas at hundreds of meters per second out of the back. Well, the more momentum the rocket propels out of the back, the more momentum the rocket has going forward. Other applications. Applying a force to an object will cause them to deform, unless you're talking about particles. For instance, a tennis ball hitting a racket. The tennis ball is going to compress, the racket's going to compress a little bit, and then it's going to go off some distance. That average force that is exerted depends on the change of momentum over the change of time. You can rearrange this equation to find that change of momentum, which is force times time. And by definition, impulse is force times time. So change of momentum and impulse are two ways of saying the same thing. If you find the impulse of something or you find the change of momentum, it's the same thing for our purposes. If you were actually able to graph what a change of momentum or impulse looks like, you would have a force times time graph, and the area in the shaded region would be the product of that. This force times time is change of momentum. Well, it's hard to find the area under a curve without using calculus, but what you can do is just take the average force times time to find the change of momentum. And I know I'm going kind of quick, but I'm thinking this is kind of a recap of stuff you've heard of before. Collisions and impulse. Impulse tells us we get the same change of momentum, whether you have a large force acting over a short period of time or a little force acting over a large period of time. And also, when you have a collision, the impulse on each object is the same. Just like Newton's third law, for every force there is an equal and opposite force, and also the two objects have to be in contact for the same period of time. Therefore, the impulse of A equals the impulse of B. The only difference is the change of direction. One's in the positive, one's in the negative. Two types of collisions, elastic and inelastic. Which type is it when the two objects stay together? Is that elastic or inelastic? Inelastic is when they stay together. Give you just a minute to read over this. All right. With inelastic collisions, there's always some change of energy. The kinetic energy decreases based on what you start with versus what you have, because there's always a loss of energy. Like I mentioned, the objects are going to deform a little bit. You're going to lose energy in the form of heat, sound, light, something. The only time you have a 100% elastic collision is when you're dealing with particles. That's all. And this picture looks kind of like an example we're going to do in a minute, where you have a conservation of momentum, and the block is going to swing up to some height, and we can solve for that. But before we get to that example, let's try some on momentum and impulse. For these examples, some of them start off pretty simple. You can probably just start typing in the numbers in your calculator and you'd be okay. But as the problems get more complicated, pictures sometimes help. So I'm going to start off by drawing a picture for each one of these just to clearly illustrate what it is that we're doing. So for instance, we start off with a baseball traveling at some velocity, 34 meters per second. Then that baseball gets hit back towards the pitcher at 38 meters per second. Now, if the ball going towards the pitcher is 34 meters per second and gets hit in the opposite direction at 38 meters per second, what should we do with one of those velocities? We should make it, or we are going to subtract, but we're going to make it negative, right? Because they're in two different directions. Velocity is a vector. One direction's got to be positive, meaning the other one's got to be negative. I usually make the initial direction positive, opposite direction negative. So this would be negative 38. So if this is 34 meters per second, then this is negative 38. Why can't I just leave it positive 38? Well, then that would be 38 in the same direction. The batter didn't have the pitch come in and then hit it even faster in the same direction. He hit it back in the opposite direction, meaning it's now going in the negative direction. So now, when we're finding the change in momentum, we can find the change of momentum a couple different ways. One is by doing mass times change of velocity. The mass of the baseball doesn't change, so we've got a mass 0.145 kilograms. Left off 5 there. Times the change of velocity. This is where the direction does make a difference. If you just took 38 minus 34 and got an answer of 4 meters per second, that's not enough. The velocity changed by a lot more than 4 because it went from 34 to 0 to 38 in the opposite direction. So anytime you find the change of something, you look at the final minus the initial. So we've got negative 38 minus 34 meters per second. So your overall change of momentum .145 because kilograms are the SI units for mass. 10.44, and I'm going to make it negative because the momentum has changed in the direction of the negative. It's going back towards the pitcher. So our change of momentum, 10.44 kilogram meters per second in the negative direction. And there's a part B that then says the ball's in contact with the bat. So the two are in contact for 0.15 seconds. What was the average force exerted during that time? Well, the force equals that change of momentum over the change of time. So we can take the change of momentum that we just found. The change of momentum is negative 10.44 kilogram meter per second, divided by time of 0.15 seconds. To get about 69.6 newtons. And I left that as negative because the net force is in the same direction as the change of momentum. This force is the reason why the momentum changed in the negative direction. Okay, so momentum is mass times velocity. Impulse is another word for change of momentum. Force can be change of momentum over time. Okay, okay so far? Any questions on that? All right. I have a skateboard one here, so I'm going to draw a picture on the board again, illustrating what's going on. Okay, so you're starting off at rest on a skateboard holding a box. You have a combined mass of 63 kilograms. You, 55 kilograms, throw an 8 kilogram mass forward with a speed of 15 meters per second. So if you're at rest on a skateboard and you throw something forward, what's going to happen to you on the skateboard? If you throw something forward, you're going to go back. You're going to roll back, right? Whatever momentum you give this object forward will result in your momentum backward. So this momentum forward is 8 kilograms times the velocity, if we call forward the positive direction of 15 meters per second, will result in your momentum backwards, and your mass now is 55 kilograms. You no longer are holding on to the box. And if you do that, you find out that you're rolling now about 2.18, about 2.2 meters per second backwards. Or more commonly called negative 2.2 meters per second. Because the negative is important because it implies the direction. If you left this as positive, that would mean when you throw the box forward, you're now rolling forward at 2.2. But that's not what's happening. If you throw the box forward, you're actually rolling backward. One of those directions has to be negative. You could make this 15 meters per second, say you threw it forward at negative 15 meters per second, then your recoil velocity would be a positive number.
Is that a V1?
It is, well, that's a V prime. It just means the velocity after. If you don't like that, you don't have to put that. All right, so box cars. Sometimes there are those empty box cars that are like on rail, like trains. Train's actually the engine part, not the train's the part that's pulled by the engine. Yeah, the train's not actually the whole thing. You got the engine, you got the caboose, but the train is the part that's actually pulled. No relevance to this question, really. I started off by simply illustrating what's happening in the problem. 7,800 kilograms is the mass of the first car, rolling at a speed of 8 meters per second. So I have 7,800 kilograms rolling at 8 meters per second. Colliding with a second box car, initially at rest. We don't know the mass yet, we're looking for the mass, but we know that it's at rest to begin with. Once they collide and roll off together, they move with a speed of 3.2 meters per second. So we know the total mass will be 7,800 plus that m2 times the velocity. So this is where it starts getting more important if you can illustrate the picture, because it might not be as clear what it is you're supposed to do here. But in any conservation momentum problem, you're just doing m times v plus m times v, and you're setting the momentum before equal to momentum after. I'll just write out the steps here. 7,800 times 8 plus m2 times 0, so that's just going to go away, equals the total mass of 7,800 plus m2 times 3.2. And just for the sake of math, I didn't write out all the units, but you certainly could to follow your dimensional analysis. So 62,400 kilogram meter per second, plus the momentum of the car that's at rest. Anything at rest is going to have a momentum of 0, equals, to get M2 by itself, you first need to distribute this 3.2. That's one way you can do it. You can do it in different orders, but as long as you can do your algebra, you're good. So if you do it this way, you can subtract the 24,960 from both sides, divide by 3.2, and I get a mass of about 11,700 kilograms.
Should it? Or does the 2 beside the M just mean the same?
Yeah, that's a little subscript. That's like M2, it's not like squared or anything. It's just a little 2. Mass 2, there you go. Mass 2, mass B. You can call him Frank. It really doesn't matter what you call him as long as you're consistent. Alright. So this was an example of a collision problem where the two stay together in an inelastic collision. Let's look at an example where the two objects do not stay together. So again, give you a chance to read over this. I'm going to illustrate or read on the board what's going on.